Okay, quick little bit of liquid solids and intermolecular forces. Some of this I think will be review and familiar. I'm going to try to not go too slow through it. This is a fun image, and there's a still, I think, from a video and a link to a video for water. If you're up in space, like on the International Space Station, it just forms a nice little orb. We're going to be learning a little bit about why that does that. So our intermolecular forces are attractive forces that exist between all molecules and atoms. Every molecule and atom has intermolecular forces. They are only significant, and even then they're not necessarily always significant, at short distances. So like touchingly close is often how I describe it. So close enough that they can reach out with their electron arms and punch each other. Intermolecular forces are responsible for some things like liquids and solids, and it's the reason that we're alive, partly. The state of a sample of matter, just anything, depends on how strong those intermolecular forces are relative to the amount of thermal energy. So if you've got something with really strong intermolecular forces and not a lot of thermal energy, it's more likely to exist in like a solid or a liquid state. If you have really weak intermolecular forces or just a ton of thermal energy, if it's really hot, it's more likely to be a gas. Our three phases of matter are very different in some ways. So the densities of solids and liquids, because all of the molecules or atoms are touchingly close, they're right next to each other, there's no empty space between them, they have a much higher density. They also have a much higher molar volume. Gas has a lot of space in between it. And there's that touchingly close again. In this molecular view of gas, there's probably not enough space between the molecules. But it would look weird if there was just one in the image. A big difference between solids and liquids is how free the particles, the molecules, the atoms are to move around. In a liquid, atoms/molecules move past each other / around each other. In a solid, they are stationary, they are locked in place. They're not moving around each other. One of the analogies that I like for solids is people at a movie theater, or y'all in the class. You have a seat. You've sort of assigned yourself a seat in this case. Some of the movie theaters, you have an assigned seat, or you just go in and you sit down, right? You're in your spot, and for the duration of your movie, you're up and around, you're running around, you're switching spots with your neighbors, you're dancing, you're singing. No, you're not doing any of that. You're sitting in your spot. You might be eating your popcorn. You might lean over and chat with your neighbor, but you're stuck in your position, right? And then the movie ends, and then you become a different phase of matter. So you're in your spot, but you're still moving around. You're not like fully restrained by some sort of Jedi mind field. And so that's like a solid. Our liquid, on the other hand, this is more like being at the front at a concert. You're all kind of jammed in. You're touchingly close, probably closer than you'd like to be with some people. But you can move around each other. You can try to push your way up to the front, and then people will hit you in the face with their elbows because they don't want you to be in front of them. And if you really need to, you can leave and go to the bathroom and then work your way back in. You're not forced to be in a specific spot by the people around you. You're not constrained. And because of the ability for things in the liquid phase to move past each other, they can assume the shape of the container that they're in. Because they can move around each other. Otherwise, you have solids, which are just a fixed shape. If you heat them up enough, they get enough energy that they can melt and turn into a liquid and then move, but otherwise they're stuck in their shape. Gases are compressible. If you've ever drank a plastic water bottle and squeezed it or like twisted it until it got really high pressure, and then you flick the cap off and it shoots up into the air or into your friend, right? You're compressing the gas, you're increasing the pressure in the little plastic water bottle that you have so that you can send that cap flying. Liquids and solids, on the other hand, are not compressible. So if you squeeze a solid, if there's air in there, you might just collapse the structure. Like if it's a piece of wood, you might collapse the structure and force some air out. Liquids are not going to have very much air in them at all. Hydraulic presses use liquids because they're not compressible, but they do flow. So you can get a giant surface area and push on it, and then force all of that pressure out into a tiny little hole. So you're taking that large force and you're shrinking it down to a small force. That's how hydraulic presses work, but you didn't think you'd learn that today. Or maybe you already knew. For solids, we've got crystalline solids, like crystals. An example of a crystal is quartz. The reason that crystals look the way that they do, the reason that they're nice, the reason that they reflect things like gemstones and stuff, is because of that regular repeating order and some other details about them. Amorphous solids do not have long-range order. So glass is an amorphous solid. You can form it into nice panes. Quartz and glass have the same chemical composition. The difference is that quartz is a crystalline solid. It's well ordered. So it's got these repeating patterns. If you took a really high power microscope and you took a picture of one section of quartz and then you scrolled over a couple nanometers and took a picture of a different spot on the quartz, you would probably find ways that those two images could overlap. If you did the same thing for an amorphous solid, you would probably be taking pictures for the rest of your life until you found a set of two images from different areas that looked exactly the same. Of these three states of matter, which is compressible? Bonus, why? Gas is compressible. You can hold it in. Why is it compressible?
Because the molecules have more room to move.
Yeah, there's empty space. Compressible because of the empty space between the particles. So you can push on them and it just shrinks the amount of space that they have. You're just restricting their freedom a little bit. It's sort of like if somebody came in and said, hey, I need this classroom right now. I'm going to have to put you into another classroom, and then they shoveled us like into my office. If you haven't been to my office, which most of you haven't, it's small. It's not big enough for the entire class if we were all here, but since it's just the 6 of us, we could all squeeze into my office. It would just be a little bit less comfortable. We would probably be about touchingly close, right? We could reach out and touch somebody like the Beatles said. Whereas in here, we've got a lot of empty space. So we are sort of in a gas state. We could be compressed down. I could have you all sit in one row. Whereas in the solid and the liquid, you can't really compress anymore. If you try to squeeze the people at the front of a Kendrick concert or something, I'm assuming there's people in the front at a Kendrick concert, they're as close as they can possibly be because they all want to be as close as possible to Kendrick Lamar. So some of the changes in states you should be familiar with. The changes in states, not necessarily their names, but you can move things from a solid to a liquid by heating them. It's like melting ice. And you can also move things from a liquid to a gas, again by heating. Like boiling water. What you're doing when you're boiling water, one of the things is you're turning that water into water vapor. And you can also do the opposite. You can cool down water vapor. That's the condensation that you get on your windows, especially this time of year if you have single pane windows. And if you cool down a liquid like water or lemonade, or coffee, you can turn it into a solid little lemonade ice cubes, for example. And changes in pressure can also cause changes in the gas and the liquid state. If you add enough pressure to a gas, you don't have any space for the gas particles to move, and they'll end up being forced into a liquid state. You can't really do the same. I think you can, but you can't really do it basically for liquid to solid because they're already touchingly close. You've taken advantage of this change in pressure if you've grilled with a propane grill. Most outside grills are propane. So you get one of these gas tanks. It's full of liquid propane, and it's stored at like 100 to 200 psi, so somewhere in the range of 10 atmospheres, to keep that petroleum product, that propane, a liquid. The psi thing is just fun, I thought, to look up. And then when you open it with the valve, hopefully hooked up to a grill, that gives the gas a place to leave. There's always going to be some gas in here that leaves, and that opens up new room for the liquid propane to form the gas. And maybe you've noticed if you've grilled for a long period of time, you touch the tank and it's cold. And that's one way that you can sort of tell how much you have left in there. And that's because of the energetics of evaporation, which we also talk about in this chapter. Above, we have a sample of liquid water. Which of the diagrams below, not drawn to scale, best depicts the vapor emitted from a pot of boiling water? We've got a guess for A. Any other guesses? It is A. Why is it A?
Well, the movie freely, but there's still H2O. We didn't change what the thing was.
Yeah, it's still H2O. In B, we've broken it into oxygen and hydrogen gas. And in C, we've got individual atoms flying around, which that's not going to happen. So it's A, yeah, because we have H2O molecules still. All that we've done is spread out the water molecules. We've introduced space between them. And we'll pause here and then pick up in lab.